Hello all, welcome back to this video on branch and bound application in traveling salesman's problem. So, what is traveling salesman's problem or widely known as TSP? Imagine a salesman, sorry. A salesman who needs to visit a list of cities exactly once and return to where he started. Okay, this is the traveling salesman's problem. What is the goal? The goal is to find shortest possible route that connects all the cities. Simple to describe but extremely hard to solve. Now, going through the definition. The traveling salesman's problem asks, given a set of cities and the cost to travel between them, what is the shortest possible route that visits each city exactly once and return to the starting city? Okay. Why is TSP so hard? Because the number of possible routes grows very fast as more cities are added. So as and when the cities are added, okay, the number of possible routes grows very fast. For just 10 cities, there are over 300,000 different ways to complete the tour. Okay. This makes the problem NP hard. What is NP hard? Non-deterministic, polynomial, time complexity. Okay. So, as the number of cities grow on, the possible routes also grows factorially faster. So, this makes the TSP and NP hard problem. So, now how branching and bounding uses to solve the TSP problem efficiently? Okay. Instead of checking every possible tour blindly, branch and bound uses a smart search method that builds path step by step and cuts off the bad path early. Okay? Instead of blindly checking each and every possible tour, instead of checking blindly each and every possible tour like in brute force algorithm, the branch and bound uses a smart search method that builds path step by step. What are we doing? We are building paths step by step. Okay, and cutting off bad paths early. Okay, we will cut the bad paths at initial stages only. Okay, called pruning. That is called pruning. Okay. So, we'll go step by step. First step is branching. At each step, we extend the current path by trying to visit an unvisited city. For example, my path is like A, B, C and D. So at each step we extend the current path by try visiting an unvisited city. Okay. Each choice creates a branch in our decision tree. So what is this doing? Creating a branch in decision tree. Okay. Creating a branch in decision tree. Next, step 2. We estimate the lowest possible cost for finishing the full tour from this path. So I want to travel from A to B, B to C, C to D. So I will check whether my travel is cost efficient when I travel from A to B, B to C and D to A. Okay. So what the second step is important. After creating a branch in a decision tree, that is extending the current path by trying a unvisited city, we will estimate the lowest possible. Initially we will estimate the lowest possible cost of complete tour. Okay. So we can either go like this: A to C, C to B, B to D and again D to A. But initially we have selected this branch A to B and now we will calculate the lowest possible cost to complete the tour: A to B, B to C, C to D and D to A. Initially we have given that each cities are mentioned with the cost of travel between them also. Okay, cost of travel between them. So either I can go from A to B, B to C, C to D, D to A, or I can go with A to C, C to B, B to D and D to A. We will initially only check the cost, estimate the cost, and if it is worse than the initial cost or an optimal solution, then we will prune it. Okay. Now we will look into the other steps. So now we will estimate the lowest possible cost for finishing the full tour from this partial path. We have selected the partial path as A to B. This is called partial path. This is called the lower bound. Okay. What is this low estimate is called? Lower bound. Lower bound. A best case guess of how cheap this path could go. Okay. What is the lower bound is named as best case guess. It is nothing but best guess, that is how cheap the path could be. Now comes the smart part. If this bound is already worse than the best complete tour we found so far, we prune the branch. So after taking the partial path A to B and completing the calculating the lowest possible cost or the lower bound, after taking the partial path A to B and calculating the lowest possible cost from A to B, B to C, C to D and D to A, if this lower bound is worse than the best tour we have found so far. Initially we have a small estimation. If this lower bound is worse than the initial case, then we will prune it, or else we will update the path. Okay. Now we will see with an example here. So in this example, first is at each step we extend the current path. For example, I have A in my current path. By try visiting to an unvisited city, so I will visit from A to B. Each choice creates a branch in our decision decision tree. So this is my branch now in the decision tree. Next, we estimate the lowest possible cost. First thing I estimate is lowest possible cost. Okay, for finishing the full tour. From this partial path. That is A to B, and I will calculate from A to B, B to C, C to D, and again D to A. Okay, this is my lowest possible cost. Now, this is also called as lower bound, which is also known as best case guess of how cheap this path could be. Okay, these are all synonyms, but the concept is similar. First we'll select the partial path and then we'll calculate the overall lowest cost for the full tour. The matter is as simple as that. Now, coming to the smart path, if this lower bound is worse or lower bound is greater than what we have calculated initially, then we will prune this branch. Then this branch is rejected. Okay, pruned. Then we'll go with another partial branch, that is A to C, C to B, B to D, and D to A. Then again, this is second case. Then again we will calculate the low possible cost and we'll compare with the first initial path. Okay, first initial path. And then if this is also worst case, second case is also worst case, then we will go with another path, that is A to D, D to B, B to C, and C to A. Okay, this is my third case. So I keep on calculating which is the lowest possible cost, and I will keep on pruning and taking efficient low cost solution. Okay, I hope everything is clear with this figure, and even I have mentioned the cost also to travel from each city. Okay, so now what is the search strategy? Until when we keep on going searching like this? There is an end for everything. So we keep exploring only promising branches. Initially only we are calculating the low possible cost. So we keep exploring only promising branches that lead to efficient solution. We'll select only promising branches and explore one by one. So if you see from A to B, B to C, C to D, and D to A is very much costly. 10 plus 20 plus 15 plus 10 is very much costly. A to B, that is A to C is 5 and C to D is 15. So 5 plus this partial path makes our problem easy. Okay, so A to C, C to D, and again D to B, and again A. So we keep on trying like this. Okay, and we'll select only optimal solution. So what are the key points? The lower bound is just an estimate. Always the lower bound is just an estimate. but a powerful one, often calculated using techniques like cost matrix reduction or minimum spanning trees. Okay. We have done videos on minimum spanning tree and cost reduction, reduced cost matrix also in my previous videos. If you want to check, go ahead with the videos, previous videos. So the lower bound is an estimate, but a powerful one, often calculated using cost reduction matrix or reduced cost matrix. Anything is fine. Just we'll go ahead with only general terms, that is cost matrix reduction or minimum spanning tree is used to calculate the lower bound. So bounding and pruning help reduce the number of paths we need to explore drastically. So at the initial stages only, we are discarding. Initial stages only we are discarding. Initial stages we are discarding. Initial stages we are pruning. So we don't need much time to calculate the whole tour. So this reduces the number of paths we need to explore. Dramatically reduces the number of routes need to be examined. So branching and bounding guarantees the optimal solution always, but is much faster than checking every other possibility like in brute force algorithm. Okay. Thank you.